Hello, everyone. Thank you so much for joining me today. My name is Shannon Holmes. I'm a medical physicist with Standard Imaging, and I have the pleasure today of being able to talk to you about some of the nuances and challenges of small field dosimetry. Let's see if this will advance. There we go. So let me start out first of all by just saying that our Standard Imaging family really wishes you all well at this unprecedented time. Our hearts go out to you, your families, your patients. We hope that you can find some peace, some joy in your daily lives amongst all the craziness that's going on right now. We're very grateful for the work that you guys do. We know your patients are very grateful for that as well. And we are very proud to be supporting you in providing the best care that's possible for your patients. Just a little bit of housekeeping before I really get into the fun physics part. We are recording the webinar today so that you can, if you have to step away, you get interrupted, your internet crashes if you're working from home, whatever happens, you'll be sent a link to the recording later on, so you can go back and see the parts that you missed or look at something again. If you have questions at any time during this presentation, please feel free to enter them into that question dialog in the GoToMeeting box. If I don't get them at the time you enter them, I will certainly circle around at the end and try and get back to any questions I may have missed. If you're not so familiar with Standard Imaging, we are based in Middleton, Wisconsin, just outside of Madison. Standard Imaging was founded a little over 30 years ago, and from its humble beginnings, we have grown to a company that designs and manufactures a full suite of QA products for radiation therapy. So I'm focusing on just the small field, mostly detectors this time, but we have the phantoms, we have water tanks, we have software, we have all kinds of other things to support your QA needs. So, to the topic at hand, what makes small fields so very challenging? And seems funny to start here, but it really is the size first and foremost. There are other issues that, of course, come along with that, like source occlusion or the changes in energy that come with the decreasing field size, changes in the shape of the penumbra and how that's defined, of course, loss of lateral charge particle equilibrium. I'll go into a little more detail on some of these, but I want to start by saying that there are a couple of really excellent references, and a lot of the stuff I'm going to cover comes from both the IPEM report 103 on small field MV photon dosimetry, as well as the joint publication from the IAEA and the AAPM, TRS 483, which is the dosimetry of small static fields used in external beam. Both are absolutely excellent references. So what makes a small field? TRS 483 gives us an actual strict definition, which helps a lot. It has at least one of the following conditions: either loss of lateral charge particle equilibrium on the beam axis, partial occlusion of the primary photon source by the collimating devices on the beam axis, or the size of your detector is similar to or large compared to your beam dimensions. One of the first challenges, of course, is physical size for small field. Usually these range from 4 to 40 millimeters in size, but of course that's a little bit energy and detector dependent as well, as we've noted from the definition on the previous slide. So one of the things that you have to ask yourself first is, how are we defining these field sizes? Is it just that you're setting your jaws at 40 millimeters or 5 millimeters or whatever these happen to be? Or are we actually looking at the full width half max of the beam? This image from Andrew Dass's publication, or from his group, kind of illustrates the way penumbras are shaped. If this is your jaw, usually lining up with the penumbra at 50% on either side for larger field sizes. But as you start to enter this small field region, your full width half max, just based on the way that these penumbras are shaped by each of those jaws, you start to overlap that shape. You start to get a wider full width half max than your jaw setting. You also get a decreased output. You can see the peak of these curves goes down. We recognize this from those output factors that we've measured for small fields, maybe with some other detectors or read about, but this is one of the mechanisms that's affecting that as well. But because of this size, the alignment of your detector becomes a huge issue. If you have a very small misalignment in a very small field like this, it becomes both a large geometric miss as well as a large dosimetric miss. And you can get yourself way off track that way. So alignment becomes highly critical as you get to smaller fields. One of the second challenges is source occlusion. So this is an image from the IPEM report that shows just the shape of the photon source and where that's visible in larger fields, whereas as you close in those jaws, close in those MLCs, or put collimators on, you may be actually blocking some of this primary source at the central, or the view of that full primary source at the central axis, which can affect your detector response, especially for detectors that have energy dependence. You're also reducing the scatter, obviously, but small enough fields reduce that direct beam fluence as well. So that's both factors come into play with the decreasing output in small fields. Third challenge, lateral electronic equilibrium. Technically, your equilibrium condition is when your lateral scattering distance is equal to or greater than the range of your electrons. If we give this a little bit more of a plain terms translation, you're going to start losing your lateral equilibrium when your beam width is less than 2 times your Dmax. So the higher energies do lose that plateau sooner. That's kind of illustrated in the plot here. Whereas you go up in energy, it doesn't take as small a field. It's a bigger field, I guess, where you start to lose that equilibrium, lose that plateau. So your detector positioning, your perturbation corrections, everything comes into play sooner for higher energies as you're working down in field size. So it is important to characterize for whichever energy field you're looking at, not just output factors, but your profiles as well, so that you can take that into account. The next thing on my list when I'm thinking about small fields is, how do my detectors impact my measurement? So first and foremost, there's of course detector size and shape that affect your volume averaging. The plot on the right here is from a publication by Meltzner and DeWord a number of years ago, where they were looking at gamma knife helmets and had a small detector in the gamma knife field, kind of expecting that within this 8mm helmet they would have been fine. They're within the plateau region for that active volume of the chamber, and only for the smallest 4mm helmet on that older gamma knife did they expect to have some volume averaging issues. Well, it turns out that not only does that active volume, my mouse keeps disappearing, there goes my active volume matter, but also the exterior dimensions, the lateral buildup, as we said, for the charged particle equilibrium, but those lateral dimensions do come into play. So even though that active portion of your detector is inside, because you're perturbing the beam there, you're putting in some air volume, and you're not just measuring the particles that are generated here, you're measuring those particles that come in from the side. The actual exterior chamber dimension does matter quite significantly. Next thing about volume averaging is, are you accurately determining your beam penumbra? If you're averaging over a larger area on a steep penumbra, you can return a result that looks a little bit more smeared out, a little broader than the penumbra actually is. Consistent and accurate positioning of your detector is critical. A lot of people use film to look at the profile shapes to help determine the volume averaging for their chambers based on that profile. If you're going really, really small, and I guess I've only personally run into this with brachytherapy sources and film, but there may be some scatter within the scanner itself that affects the resolution of the film when you're looking at a very small dot on a film. I think some of the newer scanners or newer films don't suffer from this quite as much, but there is a limitation on film as well when you're talking about an extremely small field exposure. Another way that detectors impact the measurement, I guess I alluded to, is the perturbation of the beam simply by virtue of the fact that you're putting something in the beam that is not water. You are altering the way that the electrons are set in motion. You're altering the fluence right there at the point you most want to know it. And so there are a few questions you can think about. There are some publications that talk about some of these corrections, but for an ion chamber, how big is that air cavity? How big a volume am I perturbing, and how small is my field compared to that air cavity? If I'm using a diode, it's more dense than the water. Some diodes have what built-in compensation. The compensated diodes often have kind of an air gap, or usually an air gap, I should say, to help balance out the higher density of the diode itself. You should understand, if you do have a compensated diode, how that response varies with energy, where that compensation was designed to work best, and use the detectors as intended. The key with published corrections, though, is that if you're going to be using these published corrections, you should be matching the conditions under which the authors were evaluating the detectors, whether that's measured correction or calculated correction. It's key to match those published conditions. So this is an image from Paulo Franciscan's paper in 2011, just indicating the KQ factors. As you're looking at ionization chambers, you have to correct with factors greater than 1 to account for that decreased number of interactions, the decreased density of the air. For higher density items like diodes, then the correction factor is less than 1. So another plot from a different paper from the same group, looking at again diodes or solid state detectors. There's our scintillator here, and then ion chambers as well. So there are some references out there. This was for a 5mm collimator. There are places to look for some of these corrections. The third way that we're looking at detector impact on measurement is the detector signal itself. With ion chambers, as you get down to very, very small ionization volumes, your signal decreases as well. So your signal to noise ratio becomes more of a concern as you get down to these smaller fields. And with small fields, with these small signals, I should say, you need a very sensitive and accurate electrometer to be measuring them as well. For diodes, you do get a larger signal than for micro-ionization chambers, so the SNR is not usually quite as much of an issue for those chambers. In order to decrease your SNR as much as possible, you want to make sure that your electrometer has been warmed up fully. You check it so to make sure that you're not getting leakage from the electrometer itself. It's important to match the signal strength of your detector to the proper electrometer range. If you're saturating your low rate range or you're way down at the bottom of your high range, you're not going to get as good a measurement. One thing that I learned actually from one of our engineers at Standard Imaging is that there are some additional effects from the triaxial cable that I would not have known about, both from the chamber and from longer extension cables. Obviously, there's cable-induced signaling due to irradiation. I think most of us learned that in graduate school. From Compton scatter off the central electrode, you can get some induced signal that way, some stem effect. But there's also some triboelectric effects in the cables. So if you have a tightly wound cable and you've just unwound it and laid it down through the on the floor of your vault, it may take a little while for that cable to relax and not generate these triboelectric effects anymore. So if you've got a system, you've just rolled out the cable because you want to do some quick measurements, and you're using an extremely small detector, small ionization chamber, making a very small current, and you don't have, and your system just won't hold at zero, it may actually be your cable and not so much your detector or your electrometer. Accuracy for detectors, you should have a good sense for how accurate your detectors are. Do they have energy dependence? For diodes, they can often give a lower response out of the field in those low signal strength areas, just with the changing energy out there as well, which can lead you to underestimate the low dose regions in your stereotactic patients. Be aware if your diode is compensated or not. We touched on this. It could be a good thing. It could maybe not be so good, depending if you're trying to or using it in, again, those scenarios for which they were designed. Corrections for your detector, especially one that has some energy dependence, may be depth dependent. Changes in scatter conditions, again, affect that response, especially for those detectors that have a little more energy dependence. You should be aware if your detector has any angular dependence. It's fairly critical to use it in the orientation it was designed to be used in, or correct for that. Be aware of the implications of using it in a different orientation than it was designed for. Some detectors as well have dose rate or dose per pulse dependence. This requires understanding both your detector and your accelerator, knowing that if you up the dose rate, either so you can scan faster or just because you're characterizing a higher dose rate beam, you should know whether your accelerator increases the dose rate by producing more pulses or producing more dose per pulse, because that can affect the response of your detector as well. And matching, again, the published corrections that you have for your detector with the conditions that were used, maybe even the brand and type of machine that was used, if it's measured corrections or simulated. And others. I guess I've touched mainly on the ion chambers, diodes, those sorts of detectors, but there are OSLDs, there are TLDs, there's gel, other types of film, scintillator, of course, that we offer. Each of those has strengths and limitations. Some you need to consider if there's leakage or drift, how repeatable the detector is, what's the resolution, whether it's a calibratable detector or whether it's just going to give you a relative response, qualitative sort of response. All these things also can impact your measurement. So what's a poor physicist to do? Sometimes we feel like we're just staring at a puzzle. Sometimes it feels a little bit more like a ticking time bomb when you've been handed the task of get this SRS program up and running because I want to treat, says the physician. So what do we do? Well, luckily, I think we have a few options for you. First, of course, established technology, known perturbation issues with our diodes, the D1H and the D1V. We have some newer technology in our plastic scintillation detectors. And we have the old standard, the ionization chamber, finally working properly in miniature form in our Exradin A26. So we'll talk a little bit more about these. Remember, each detector, every detector you get from any vendor, not just from Standard Imaging, has both strengths and limitations. Your best solution really is a good combination of detectors so that you have a good balance between those strengths to balance out the limitations of the others. So about our diodes, the D1H and the D1V, it's the same diode, just in two different orientations. So the horizontal D1H is designed for to be able to be put in slab phantoms so that you can mill out a channel for that pretty easily. The D1V is the vertical orientation designed for scanning. These are both unshielded diodes, well, same diode, unshielded. It's a 1 millimeter diameter spot size for those, and there are published corrections available. There were 2 publications in 2014 that looked at both measured and calculated factors for these. One of those here is from Papakonstantopoulos et al. In PMB. But looking at both the W1 scintillator as well as the diode here compared to the microdiamond. Looking at field sizes. I don't remember the energy on this particular beam. Paolo Franciscan also looked at it. We saw this plot earlier, but it does include the Exradin diode. Strengths of this, as I mentioned, it's a well-established technology. People have been using diodes for quite some time. They're well known, they're understood, despite the fact that they need corrections. You can use them in your scanning water tank to look at field shapes. Have minimal volume averaging just based on the size of the detector. Low angular dependence for our diodes. There is some if you get pretty far off axis, but they're pretty good for angular dependence. Limitations of diodes are that they are not water equivalent. As I mentioned, they do require some corrections for that different density. And there is a little bit of angular dependence. If you're trying to do arcs with these, then you might find that you get a little bit different response with that. But if you're just scanning end-on in your water tank, then they're fabulous for that. The second option that I had mentioned is that new technology, the Exradin scintillation detectors. We have two versions of it, but it's an organic scintillating material, either 1x1 or 1x3 for the active region. They are fully water equivalent for MV photons and electrons, which is very nice when it comes to those correction factors that are really energy dependent correction factors. They do require correction for the Cherenkov light that's generated within the optical transfer fiber. And they are not absolute dosimeters. They're not something that you can send into your calibration lab and get a cal factor for it that's going to last you a couple of years. They do degrade with age, like all plastics do under radiation. And so as your signal decreases with that yellowing of the plastic, you do need to recalibrate periodically just to account for the decrease in signal as well as the slight change in that spectrum that's transmitted through the coloring fiber. We use a 2-channel chromatic correction for that Cherenkov removal. It's based on a publication by Matthew Guyot from 2011. And what they describe in that manuscript is splitting up the scintillation region into a blue region and a green region. Our scintillator really is a blue scintillator. The Cherenkov spectrum is a broad spectrum. So we have you do 2 characterization measurements. In a slightly larger field. This is the slab that comes with the W1. We would have you do a minimum fiber configuration with the fiber coming straight out of the field and a maximum fiber configuration where you wrap the fiber around and irradiate more of that fiber. The idea here really is to keep the dose to the scintillator the same and change only the Cherenkov contribution. So if you can do that, then you can look at the change in the signal in both of these channels and create a correction factor called a CLR, Cherenkov light ratio, that can be used in subsequent measurements to remove the Cherenkov contribution in the green channel, or excuse me, in the blue channel based on the signal level in the green channel. You can also give it a dose calibration yourself. You can cross-calibrate with something that you have in-house. We have a 10x10 field marked on these slabs, but you can use 10x10 or 5x5, whatever sort of daisy chain if you want to do it that way, to give it a known dose in a known field size at a known depth, and then the subsequent measurements can be discussed in terms of dose. The question is, how do you do the Cherenkov correction for the scintillators? With the W1, we have a 2-channel output from that one. The W1 has just the optics, so it needs a 2-channel electrometer like our Supermax in order to do the measurement, so you can get both channels at the same time. And then the Supermax actually has the routine built into it, both for you to do the characterization measurements and save those, and it will calculate your CLR. And then when you measure in scintillation mode later on, it will take that CLR that you've selected and apply it to the measurement so that it can give you your output either in terms of a corrected charge or the dose calibration. It'll convert to, if you do a dose calibration, it will convert the results to dose as well. The W1 was the first generation scintillation detector. It does have a 1 millimeter diameter, 3 millimeter long active scintillation region. And it's been on the market for, oh goodness, quite some time now. So there are a number of publications about the W1, but the TRS 483 publication lists the W1 KQ for a lot of different detectors for a number of different energies. This is just one of the tables in there, but I like to point out that the W1 in every table it shows up in has correction factors for all field sizes of 1. It's all unity, and it's the only detector in this publication that that has that. So it's actually very nice that you don't have to worry about those field size dependent energy dependent corrections with the scintillation detector. Strengths of the W1 are of course that KQ of 1. It is water equivalent 4 MV photons and electrons, so you're not having to apply perturbation corrections for the change in the density of the detector itself. It hasn't demonstrated dose rate or energy dependence issues, and then it has a negligible temperature dependence. So if you're doing all your measurements as QA measurements, room temperature measurements, you don't have to worry about a temperature dependence. It's about 0.1% per degree. Some of the limitations of the W1 is that it was designed as a point measurement system. It was not designed for scanning or for large fields. It does have a low signal to noise ratio, so there's a higher uncertainty. If you were to try and do a point by point measurement of a field scan, you'll have a higher uncertainty out of the field in the low dose tails because you'll bump up against the noise floor of the detector itself and the cables that you have to use. It's not an absolute dosimeter, we mentioned that, so it does require you to give it a reference dose if you want output in terms of dose, and then occasionally recalibrate as the plastic ages. The other limitation, I think, of the W1 is really more of a limitation as you're first getting used to measurements with scintillators, and that is that we're used to ion chambers, we're used to using diodes, and so troubleshooting those is a little bit more intuitive to some of us than to those who haven't, or then troubleshooting a scintillation detector is. So optical signal measurements aren't completely intuitive to many users, first-time users in particular, but it has become familiar for a number of users. I know several people who are extreme fans, I should say, of the W1. The more recent scintillation detector that we've released is called the W2. This was an improvement over the W1 in that we were able to improve the sensitivity of our optics. So we were able to allow both that 1x3 millimeter detector, or you can put in a 1x1 scintillator and use it with this system. We combined the optical signal detection with the electronic signal processing, so you don't need a separate electrometer anymore. It has its own dedicated system, which we call the MaxSD for scintillation detector. This allowed us to further decrease the electronic noise by getting rid of some of those longer cables, so that we could get a better SNR from those, even from the very small size scintillator. You can perform the Cherenkov characterization as well as individual point dose measurements with the MaxSD alone. It will also perform a it was also designed to be used with water tank scanning systems, and so it does a 10 millisecond integration, performs the Cherenkov correction very quickly, and then can convert that Cherenkov corrected value into an analog output, a single analog current that can then be output to your water tank. So the water tank doesn't know that it's any detector other than say a diode. It looks like a diode to your water tank because it's not applying bias, but it's getting signal from it. And then you can collect scans with your water tank electrometer. So that's been highly useful as well. Strengths and limitations of the W2 really match the W1, with the added advantage that we've been able to get rid of a couple of those original limitations from the W1. The old standard now working well, the microionization chamber, the A26. So all microionization chambers on the market, other than this one, had been exhibiting very strange ion recombination behavior and polarity effects. And so Jessica Miller did her PhD work at the University of Wisconsin-Madison on the spurious behavior of all microionization chambers that were available at the time. And what she traced that behavior to was a mismatch in conductance between components within the microionization chambers. And so as a result of her research work, we designed the A26 to eliminate those behaviors. And it is the only microionization chamber on the market that actually behaves properly when it comes to ion recombination. So it was designed to provide that reference class measurement in as small a range as, or as small a size as we could possibly make for ionization chambers. So when we were designing this, there were several questions that we were looking into. What should the spot size look like? And we really wanted to make a spherical collecting volume so that we didn't have any orientation issues when you're looking at volume averaging in the field or scanning cross plane versus in plane. You don't have to turn the chamber, but it's all uniform that way. We modeled the electric fields on the plans that we were making in order to verify that we were really meeting this this design need. Having problems with words today. Design constraint. We were trying to really meet that target. The chamber volume we wanted to make as small as humanly possible, really. We're making all of this out of a uniform conducting plastic, and this really is the smallest that you're going to see, I think, anywhere with a solid design chamber like this. It is slightly larger in volume than our A16, which was our prior smallest chamber, but the spot size has increased by only 0.8 of a millimeter, even though we've doubled the volume. So that really is the result of the machining of all of these parts out of that well-established conducting plastic. So then the other question we're asking ourselves is, when we get down to signals that, or to fields this small, ionization chamber this small, will we have an SNR that's sufficient for the intended use? And it turns out we do. So strengths of the A26, it has been on the market for a number of years now as well. It was designed as a reference class ionization chamber, so you should expect very good behavior from this compared to any other microionization chamber that you've tried. The spot size is independent of the orientation. That was that spherical spot size that we were designing. And the strength of the A26 also is that it is familiar technology. It's an ionization chamber. We're very used to working with ionization chambers and understanding when things go wrong with that. The limitation is just a standard limitation for any ionization chamber, and that is that it has an air cavity, and so it's going to have a perturbation correction. There's a question about whether the A16 is good for small measurements. It is good for small measurements. It's still the smallest chamber that we market, and we market it still confidently because it's a good chamber. But the recommendation from the calibration labs is that you don't apply a polarity correction. You measure at the polarity at which the chamber is calibrated. So you be consistent with the polarity you're measuring, and don't try and apply a polarity correction because they're often unrealistic. So non-physical is, and it's not just the A16. Some A16s will behave just fine for recombination, and some will show that polarity effect. It's the same with other chambers. It's not a model-specific problem. It seems to be an individual chamber problem, and that's across the board on microionization chambers. Kind of a fascinating topic, actually. I thought Dr. Miller's PhD work was quite good. So what about small kV X-ray fields? We've talked a lot about megavoltage. Just a minute, buddy. I'm giving a talk. Okay, just a minute. So the A20 is our small kilovoltage field chamber. It's a little parallel plate chamber at the tip of this, meant to be used end-on. It was designed for small fields or for skin applicators, whether that's HDR or electronic brachytherapy sources or low voltage superficial skin therapy. It has a just under 2 millimeter collector diameter, has a very excellent energy response ranging from the 20 keV, where the lowest we tested it, all the way up to cobalt 60 energies. I'd be remiss if I didn't spend at least a little bit of time talking about our electrometers. The Max 4000 Plus is our workhorse. It's a fabulous electrometer. It's a very robust single channel reference class electrometer. And it's a workhorse. It's in a lot of centers across the world, and a lot of people really enjoy using that one. The Supermax is our high-end 2-channel electrometer. It does have a touch screen with extremely intuitive navigation. Each of the channels can be controlled independently, and it has a very short warm-up. I've copied just a couple of the rate information here. The Supermax has a little bit more resolution on the low end, but both electrometers are very robust. We stand behind them. In fact, both have an industry-leading 5-year warranty. We know how to make electrometers. We've been doing it for years, and we've got a lot of them out there in the field. So with that said, we're happy to work with you to conquer that challenge of small field dosimetry. If you need any more information about our detectors, about our electrometers or phantoms, water tanks, any of the rest of it, please feel free to visit our website, poke around, or contact your sales representative at sales@standardimaging.com. I know they always enjoy hearing from people too. They're very social. It's hard for them to be locked in at home for too long. So just some contact is good. Anyhow, if you have any questions, thank you so much for your time today. I'd be happy to answer any questions if you want to enter them into the panel. There's a question about the W2. Is it restricted to just small fields? How large can we go for the large field measurement? The W2 is still also a small field detector. I wouldn't do much above 10 by 10. You can certainly go up to a 15 or a 20 if you'd like, but it really is designed for those smaller fields, and the more fiber you put in the field, the higher your Cherenkov signal, and at some point, depending how much you have in the field, you can start to overwhelm your simulation signal just a little bit, which decreases or increases the uncertainty, decreases the certainty, the accuracy of your measurement. How often do we calibrate small chambers like the A16? Chamber calibration usually is every 2 years in terms of the ADCLs. And the A16 is stable in and of itself. It's the one thing that I would make sure that you take a look at is that you're using the polarity consistently. So you always get consistent measurements from it. Is the 2-channel electrometer for scanning or just for measurements? That is just for measurements. Our scanning tanks have built-in electrometers for scanning. Although you can use I should say the 3D tank has a built-in electrometer. You can use the Supermax or the Max 4000 Plus for scanning with our 1D tank. Do we have a wireless electrometer? We do not, other than the oh, no, that's Ethernet. No. So, no, we don't have a wireless electrometer at the moment. Angular dependence of the A20. I am not sure of that. That's a very good question. I would have to look into that. I'm sorry. Let me see if I can follow up for you on that one. And do I teach any classes on small field dosimetry? I don't, but thank you. That's a very, very kind comment. It's a passion of mine. I do enjoy talking about it, so it's kind of fun to do a bit more physics-oriented talk once in a while. How does the A26 deal with lack of lateral charge particle equilibrium, or is that an issue? It's an issue with any detector, so it's not going to be just your microionization chambers. The main problem with the lateral CPE is that when you put something in the field that changes the density within the field, and that something, whether it's diode or ion chamber or some other detector, it changes the interactions and changes the lateral CPE. So the best one actually for those small fields is going to be the scintillator, because despite the lack of lateral CPE, you are actually measuring the dose that's deposited at that point. And so it's a more realistic measurement of what's going on without having all of the correction factors. Is there a setup cap for allowing easier setup of the detector for the motorized water tank scanning? I assume you mean for the scintillator. Most of the ion chambers have an alignment cap. The W1 does have an alignment cap. With the W2, we have not been sending that. It's actually a little easier with your 3D tank to set it up aligned to the tip of the scintillation fiber and then step the fiber forward in order to find that alignment. But there is there is an alignment cap available for the 1x3 for the scintillator. Question on the tank measurement. Where will be the effective point of measurement? For the scintillator, the effective point of measurement really is the center of the scintillation fiber itself. So with the 1x3 fiber for the W1 or the W2 1x3, it's 2.3 millimeters back from the tip of the fiber. And for the W2 1x1, it's 1.3 millimeters back. So that's just the physical center, and then centered on the fiber, of course. There's no vertical offset for effective point of measurement for that. And that's really just the physical center of that scintillation detector. If you have a scintillator and you scan with it, you're trying to find that point of maximum response, and you find that you're offset from that physical point, that generally indicates that you're not properly accounting for your Cherenkov. So you would want to revisit your CLR measurement, make sure that you've done that one properly. But you can also do a small cross-plane and in-plane scan and make sure that both of those look flat, look uniform, because if you are improperly accounting for your Cherenkov, when you scan in the same direction as the fiber, you'll get a slanted scan. Because Cherenkov is essentially a stem effect that you would need to remove. I think that's it for the questions I've got. Oh, one more. For the plastic scintillator, how different is it from your absolute dose measurement? So you would be measuring dose with the scintillator after you've given it a known dose, and so it really is tied to your absolute dose measurement. So after you do your calibration, say in a 10x10 field, then you would need to, if you want dose output from the scintillator, you would need to give it that known dose at, say, Dmax or depth of 5 in that reference field. And then you essentially have a conversion factor for the Cherenkov corrected signal, then is converted to dose. So there shouldn't be a difference between your W1 and your absolute dose measurement. It's more of a daisy chain. Do we observe saturation of signal for FFF beams using 2400 MU per minute? Not for the scintillators. I'm not sure. I guess I haven't looked at our chambers lately, but there shouldn't be a saturation for those either. But yeah, the scintillator works fine as well, up to 2400. We have not gotten it into flash beams yet. It'll be fun to see at what point we actually do saturate. So if someone wants to collaborate on that, send me a note. Yeah, for all of the FFF beams, it works fine. And that you can look actually back at that TRS 483 publication. The the table that I was showing actually was for, I think, 10 MB both with and without flattening filter. How low can the dose go for the W1? I don't have the number offhand. It was designed really for the in-field measurements. And I think there was a poster from the NRCC, maybe. I think it was Malcolm McEwen, who had a poster at AAPM, I don't know, 5 years ago or so, looking at scanning, step-by-step measurement scanning with the W1, and it worked perfectly fine in field, but he got higher tails on those profiles just because of the noise floor of the system. Is there a possibility to use the scintillator for proton dosimetry measurements, for point measurements there? Our scintillator, as far as I know, has not been used under protons. There has been some research out of MD Anderson about some quenching effects for those scintillators under protons. So it's not something that I can confidently recommend right now, but it could certainly be used in a research format to investigate whether that would work. Seems like we're coming to the end of the measurements, or excuse me, of the questions. Measurements yet to come. Thank you so much for your attention. My apologies for the interruption in the middle. I had my 5-year-old come to tell me something critical. And we look forward to hearing from you in the future. Take care, everyone.